All right. Fabulous. I think we're good to go. Thanks everyone for joining us. Today we've got Areeb Malik. He's a seasoned ML practitioner and generalist software engineer. After graduating from Cornell, he did 5 years at Facebook, and then he co-founded Glacier in 2019 to make a serious and immediate impact on society's fight against climate change. Glacier deploys cutting-edge ML to perform classification and detection work to revolutionize the circular economy. And they've got lots of really interesting and complex challenges, distinguishing plastic resins, characterizing truckloads of trash, automatically detecting contamination. I think Areeb also wins the prize for this year's best title, Hard Challenges in Dirty Places, a fabulous, pithy one. So today, Areeb is going to talk about their approach using ML to extract value out of the products that we consume and throw away.
I am glad to hear I win title award. I did not know I was in that competition, but I'm glad to be there.
I invented that 3 minutes ago, so congratulations.
It feels all the more special now that you said that. Cool, let me just get my screen shared. And Archie, let me know, can you see this all right? Oop. Not sure if that's coming through, can you hear me? Okay, I got a thumbs up, but Archie doesn't seem to be there anymore, so I'm just gonna relaunch that guy real quick. Hang on one sec.
I'm back. Sorry, Areeb. That
You're
worked.
back.
I just did this ducking backstage act without telling you.
Got it. Okay, well, I need to, let me pull up the presentation again. I get the best title and the worst getting my presentation up and running.
Kenji, it's literally called backstage in Zoom. So it's not just my terrible title. All right.
All right. We are showing, yes. I'm gonna take that as a yes. All right, cool. I'm gonna get started. Thank you to everybody here for showing up today. I know there's been a lot of cool talks, and I know recycling is not necessarily the first thing that comes to mind when you think of cool ML challenges. So the fact that you're here is awesome, and I appreciate you taking time to learn. I will inform you now that recycling actually is very awesome, and so you are in for a treat. My name is Areeb. As Archie mentioned, I'm the founder of Glacier. I started this company 3 years ago with the explicit mission of working on climate change and finding a way to use tech as it stands today to actually make an impact on climate change. And I'll tell you more about what we do at Glacier, but first, I have a quiz for y'all. So this is a semi-truck trailer rather, dumping a bunch of stuff into a landfill. Now in this truck, there is about 20 tons worth of waste. That is the mass that it can actually dump. And when you dump stuff into a landfill, you cannot do it for free. The landfill charges you. This landfill charges $50 per ton. So the quiz is, what is the cost of dumping this much stuff into the landfill? And if you're thinking, oh, hey, Areeb, that's a really easy question, it's because it's a trick question. Yes, there is a $1,000 tipping fee that is 20 times 50, but there's also a hidden cost here, and that hidden cost is in the value of everything that is being dumped. And this may be surprising to hear, but within that truckload of 20 tons, there's actually $6,000 worth of recyclables. That is stuff that we could actually capture out of this truck and put back into use in the circular economy. And the value of that, at least at current markets, is about $6,000. That's every single truck that gets dumped into landfill. And if you magnified this out, there is, of course, a pretty big global impact to this. If we look around the world, every truck that's dumping everything into landfill, we're talking about over $100 billion worth of recyclables. And of course, when you're doing that, it is not just the dollar figure that is stunning, but the actual impact on the climate that is stunning. When you do not recycle an item, there is a CO2 impact, and I'll talk more about that later. But every year, this amount of kind of uncaptured waste amounts to 500 million tons of CO2 emitted, and that's on an annual basis. This all comes down to the fact that we do not do a good job recovering our stuff. Globally, we only recycle about 9% of what could actually be recycled. This is a lot of problem. This is why we founded Glacier. At Glacier, we have a very explicit mission. It is to end waste. We want to do everything we can to bring technology to the sector behind the scenes to make our handling of waste much better, much stronger, so that anything that is valuable does not end up in that landfill, but actually ends up being used and put back into the circular economy. Today, we have two key products that are working towards this, both of which have a really cool ML angle that we'll talk about. Number one is the ML-powered sorting robot. I'll dive a lot more into this one in a second, but the key point is that this sort of technology helps us actually keep things from ending up in landfill if we can actually identify and pick them out more efficiently, more cheaply, etc. Secondly, if we can use machine learning, computer vision to identify stuff in our trash and just classify everything, we can actually produce analytics. And this is a really big one because this industry does not have a good sense of data. There is not really a sense of where is my trash flowing, what is in my truck, and all of this missing data amounts to a ton of mistakes and inefficiencies in the system that just now CV is getting to the point where we can actually automatically provide those insights and those analyses to make the system much stronger. Before I dive forward, I need to talk about recycling and how it works, because if you are like I was 3 years ago, this was about how I imagined recycling working, and I imagine many of you do as well. Number one, you put your recycling out on the curb, and then the truck comes over, and then like some magic happens and good happens, and out the other side, like everybody's happy. That's definitely what we're taught when we're taught about recycling, but obviously in that little middle piece, there is a lot of work going on, and it definitely pays to understand what's actually happening behind the scenes when you take your stuff out to the curb, the truck takes it away. What happens? And so I'm going to walk you through a obviously very high level overview of that, but hopefully should get a little more clarity on what's going on behind the scenes here. So number one, like I said, you, the consumer or the business or whatever, you recycle. You take your bin out to the curb, and in that bin, hopefully, is all recyclable stuff. But as we can assume, there's a lot of stuff in there that's actually not recyclable. From there, the truck comes and picks it up. And that truck's job is simply to transport, but obviously transporting all that mass is a big task. And it actually is a pretty big emitter when you're trying to move all of this weight around. The truck, the hauler, takes it over to a facility known as a materials recovery facility, or a murph. That murph's job is twofold. Number one, they need to pick out everything that you put in there that shouldn't have been recycled. And as a consumer, it's impossible to know what is recyclable and what's not. So you see a lot of stuff making it to the recycling facility that doesn't actually have an end use. And so actually it shouldn't have been put in the recycling bin. Job number one is to pick that stuff out. Job number two is to sort apart all the rest. Their objective is to basically separate all of the commodities that you put into your recycling bin, your plastics apart from each other, your cardboard, your aluminum, your steel cans, your paper, whatever it might be. It needs to all be sorted out so that something can be done with it. Out of this murph comes what's known as a bale, or a bunch of bales of a commodity. A bale you can think of as basically a compacted cubic meter size bundle of a single commodity, right? So just imagine a bunch of paper kind of compacted and wrapped in twine. And that is what they try to output from the murph. They sell that to what's known as a reclaimer. The reclaimer takes in these bales of a single commodity, and there's a bunch of different reclaimers for each commodity. So you might have a cardboard reclaimer or a PET reclaimer. Their job is to take that stuff and do something with it. In this case, in the case of plastic, or in the case of paper, basically you want to shred it down and get it to kind of that atomic base unit that you can now sell to be turned into something else. And that's where the manufacturer comes into play. This is where things get kind of interesting from a climate perspective, because as a manufacturer, you have essentially two choices. You can either make your new product using virgin material, that would be the petroleum or the iron ore, or whatever it might be, into new stuff, or you can use recycled material. And when you go with the recycled stuff, one, it is cheaper, and two, it is much more energy efficient. To give you an example of that, if you make a new aluminum can from an old aluminum can, that takes about 97% less energy than if you were to produce it from the raw materials that go into the aluminum can, the bauxite and the iron ore. That's a huge win, and that sort of is where that 500 million tons of CO2 I was talking about really comes from, is you get these energy savings when you recycle. The problem, of course, is that there's not a lot of good recycled material to buy from because we're only recycling 9% of it. And so you can see why this is a problem, and where ultimately the win can be had. I'm going to zoom into this section right here inside the kind of what happens when you put your stuff out, and how does it get turned into these bales? Because this is actually a really hard challenge that is probably one of the biggest things that this industry can actually work on today. And it has a really cool opportunity for ML to really change how it works. So let me zoom into the murph. Again, their input is everything we give them. Their output is ideally these pure bales of commodities. How do they do that? They have a couple of techniques for performing this really hard sorting challenge. Number one, if you go to the most basic murph, the really simple ones, what you'll see is a conveyor belt and people, and those people's job is to pick things off of the belt and put them into bins or chutes or whatever. That's kind of the basics of how a facility operates. Obviously, that's really tough because people are hard to find for this role. It's hard to hire for. And so facilities are constantly looking for ways to get more done with less cost. And so that's where the machines come into play. There's a bunch of machines that already exist inside these facilities. I always consider them high quantity, low quality machines. They do a great job of handling a lot of stuff, but they tend to have a pretty bad error rate on the other side. And the quality that these machines output is not high enough to actually be sold to reclaimers at a satisfying rate. And so inevitably after these high quantity, low quality machines, you have more people whose job it is to basically QC them. The third thing, which is, I may have hinted this earlier, coming around soon, is robots. And robots have this really unique ability to provide high quality sortation at a low cost. And that's been a big kind of change for this facility, or for this industry. That's something that we are definitely seeing a lot of interest in, and a lot of uptake in terms of this technology. So that's something we're going to dive into. With the machines, I should kind of caveat, like, how do they work? This is a typical machine you might see inside these facilities. It's known as a disc screen. This is, again, you're going to kind of see how this high quantity, low quality sortation works here. What this does is basically all of those rods with the kind of discs on them, they will spin and move things up this kind of slanted platform. Everything that's small is going to eventually try to find its way through those cracks, and everything that's big is going to try to find its way up and over the edge. And so you kind of get this density sortation. As you might imagine, though, a lot of things that are small, like bottles or cans, might just pop their way over anyways, and a lot of smaller crumple of paper might find its way through. And so what you intend to get is kind of paper up top, other things underneath, but you tend to not get that. This is why the QC comes into play, and why you need something else after these machines. There's some big thing missing from this process, which is where robots or people come into play. All of this being said, however, you as a facility have a lot of questions about what's happening inside your facility. Whatever people, machines, robots you have, it's really hard to know how you're doing. And there's a lot of missing questions that come from the fact that data in this industry is just sparse. So how do I know how I'm performing? How do I know if what I'm getting, the input I'm getting, is good supply? If I'm getting 95% junk, not recyclable, from my trucks, I need to know that, because that's not good for my business, and I'm just spending a lot of energy trying to produce something out of nothing. How do I know where to invest my operational improvements? If I have budget for 4 more people or 2 more robots, how do I know where to put them? And these are questions that you don't have answers to, because there's no understanding of how stuff flows through your facility, what's coming in the inside, what the quality is going out the back end. And if we zip out one level to that kind of broader picture of how recycling works, the questions multiply. If you are a city and you want to know your recycling rate for the city, how do you measure that? The best we can do right now is go into a couple of trucks and count. But if I want to know my recycling, I want to make improvements on my recycling rate as a city, I don't have any data to do that, and therefore it's really hard to make changes. How do I know where to invest my taxes to improve things? How do I know what products, what manufacturers are causing the most harm, so I can actually design legislation to stop them and get ahead of this? If you're a manufacturer and you have ESG requirements, whether you want to or the laws force them on you, how do you know how to act on your ESG requirements if you don't know where your stuff is going? If you're producing 100 million Coke bottles a year, how do you know what to do if you don't know where they're going? You're selling them, and in theory, they're all being recycled, but we know that not to be the case. So what do you do at that point if you don't know what happens after it leaves the shelf of the grocery store? And how do you have metrics to hit your ESG goals if there's no data to track everything? So there's this big missing set of data that makes this whole industry really hard to make progress in, because it's really, we have a lot of hopefully engineers or data scientists listening in right now. It's really hard to make product wins if you don't have data and metrics to move off of, and this industry suffers from that problem right now. Why is this? It's because even though the value of having this data is understood and it's very clear what it would be, the cost to produce this data is too high. To give you an example, if you are a murph and you want to know what your trucks are giving, what % of it is plastics, recyclables, diapers, whatever, you need to take a truckload off of your tipping floor. Tipping floor is just where they dump stuff at the murph, and just partition it out and just literally count how many things are plastics, put them in a bucket, into cardboard bins or whatever. And that's how you do it. That obviously sounds very expensive and very time consuming, because it is. Similarly, if you want to do the outbound, in my bale, what % is actually plastic versus stuff that shouldn't have gone in there? Again, break the bale down, manually count it. Each of these processes takes several person hours, and they're therefore really expensive. And as a result of them being expensive and hard to do, they get conducted really infrequently, and so they have very sparse data points, which is just another problem for making smart decisions. If I were to take this kind of more mathematical or scientific way, the fundamental problem is that the input data, which is bottles, cans, pieces of cardboard, whatever, is inherently non-digital. It is stuff. It's stuff you can hold, and we need data to be digitalized in order to do something with it. Right now, the conversion process of going from real stuff to digital relies on humans, right? We use human eyes and human hands to do this conversion, and that conversion cost is prohibitively expensive, and that's why we are unable to actually use data, even though we know how important it is. And this should be obvious at this point, but if you're sitting there thinking like, yeah, like ML can solve this problem, well, yeah, it can, and that's the cool thing about what is on the table for us. So I want to dive into, how do we actually solve this using computers instead of using people. So this is a picture of a conveyor belt. It's from what's known as a dirty murph. Great name. A dirty murph is basically a murph that handles what we put in the landfill bin. Anything we just throw away, do not recycle, it all ends up here, which is why you see like a shoe and a bunch of like foam in here. But there's also obviously a bunch of recyclables, and their job is to pick out those recyclables, keep them from going to landfill. If I have this picture, this is the baseline non-digitalized data. We want to get to this, right? We want to get to a point where we can actually use object detection or whatever might be the right case to identify every single thing that is in here that has value, so that we can actually take action on it. And this is a relatively straightforward problem, but it is super difficult, and I want to get into why. How do we get there in the first place? It's pretty straightforward. You take some pre-built CNNs, you take some SSD backbones or RCNN or efficient DET, you throw a bunch of data at it, and you get something like this on the right that can just kind of monitor and accurately tag things real time. This is easy in some ways, right? You have a lot of things under your control that is not typical of a ML application. You have controllable lighting. You're inside a facility, so all the light you're dealing with is yours, right? You just put some lights on and you can see. You have fixed distance to your items. You don't have to deal with any like crazy depth things, because at most the item is going to be 3 or 4 inches closer to you than normal, so nothing crazy to think about in that realm. Data is plentiful. It's really easy to just put a camera into one of these facilities and get lots and lots of images. And these off-the-shelf models, like I mentioned, are really good. Like, this technology is advancing and getting to a point where you can get some serious results just by taking an off-the-shelf model, throwing some images at it, tagging it, and letting it run. that'll get you somewhere, but it doesn't get you all the way. And unfortunately, there is a lot of value had in closing the gap between that somewhere and that all the way. I think if you run one of these models off their baseline, you'll get your F1 scores in the 80s. But what really matters here is getting that up and up towards 99, towards 100. And that is where a lot of the challenges come into play. So I want to walk through a couple of those challenges because I think this is the most intriguing part of what we do. Number one, there is a lot of variation per commodity. So you're looking at a bunch of images of PET bottles. So PET, as a reminder, if you don't know, is triangle number 1 plastic. That's what typically drinking bottles, water bottles are made out of. And you're looking at a bunch of those right here, but there's a ton of variety in this commodity class, right? So not only do you have things like here over on the top left, where you have a bunch of crumbling, right? A single bottle, the same bottle produced 100,000 times can be crumpled in hundreds, thousands of ways. But you have differences in size, right? Two entirely different sizes for the same commodity. Your bottle can be wrapped in some sort of film. It can be hidden behind other stuff. Lots of things happen that make this very difficult. It's not like looking at a car on the road, which typically looks more or less the same because cars typically don't get smashed up the way that bottles do. And this difficulty prevents a challenge for our ML models because you all of a sudden need to think, okay, I know what a bottle typically looks like, but how does a bottle look like in all possible forms? And how do you actually capture data that represents that? Secondly, you don't just need to classify by commodity. There's a lot of layered classification. And what this involves is building out really smart hierarchical classification models. And so on the right is a great picture of 3 PET containers. 2 on the left, one is Gatorade, one at the bottom seems like a water bottle. And then this thing on the right is what's known as a clamshell. It comes wrapped around like your blueberries and stuff like that. It's also PET, but it actually is recycled differently than PET bottles. And if you go beyond that distinction, it actually gets even more complicated because when you think about what a city or a manufacturer wants to know, you kind of need to classify deeper and deeper beyond just PET, beyond PET bottles, all the way down even to the SKU level, where if you're Coke and you want to know how many of my bottles are going where, it's going to be important to know what count of my 20 fluid ounce Dasani PET water bottles are making it to the recycling stream. And so this sort of information is really hard to build ML models for because it is a really deep hierarchical classification that is a little bit beyond what typical models can do today. And that's where a lot of the customization we build comes into play. Commodities are oftentimes very difficult to distinguish. So this bottle over on the left is looks like a water bottle. It's made of something known as PETG. It's a modification of PET, but it cannot be recycled with PET. And if you're looking at that with my eyes, I'm sitting here thinking, I don't know how that looks any different than a regular water bottle. So how do you actually distinguish that type of stuff? Can you use additional information from the bottle, such as the label, the brand? Can you use hyperspectral imaging? What are the techniques you need to pull in here to actually supplement what you can do with your eyes so that you can actually make these distinctions? Over on the right, same problem. We have 2 clamshells. One is made of PET. The other is made of polypropylene, which is triangle 5 plastic. Again, they look very similar to the human eye. So how do you actually create these distinctions within the eyes of an object detection model? Not easy, but can be done given the right thinking and right problem solving. Oftentimes the distinction is in the details. So here we have 2 cartons. One is for what looks like soy milk and the other looks like it's for coconut water. And these 2 look very similar, and they are in fact very similar. But the smaller one on the right, if you look down at the bottom corner, you can see this little logo. And if you're not familiar, that is the Tetrapack logo, which means that this carton over on the right actually has a layer of aluminum inside of it versus this one on the left does not. It's just paper and a plastic film. Both of these are actually recyclable, but they need to be separated because they can't be recycled the same way. Distinguishing those can be very difficult, right? You're looking for small symbols like the triangle over here, or if you can't even see that triangle because it was flipped the other way, how you distinguish those 2 cartons starts to become a very fine game of looking at the details of items. Some of the most object detection models are not great because they tend to look at what's inside the entire bounding box instead of the details in the corner of the bounding box. So how do you give weight to those kind of issues and those kind of features so that you can actually make these distinctions is another challenge that we are tackling, and it's a cool one. Occlusion, a big deal, as you might imagine when you're looking at a belt full of stuff, or if you're looking at the back of a trash truck or looking at what's coming out of a garbage bin. You don't get to see everything. You definitely don't get to see all of the thing you're looking at. So how do you build CV models that can deal with constant and high occlusion, and how do you build occlusion handling into your model, into your training, as even into your tagging is difficult because it's hard for a human eye to see that and tag it. So how do you integrate that entirely into your process? I think this is the last one, but I clearly could go on forever. The industry and the businesses that operate in this industry, they work by weight. They don't work by count. They care about tonnage. ML models, object detection, it's great at count, right? You can draw a bunch of boxes around stuff, which is all good, but we don't need count in this industry. We need weight. So the question is, how do you take that image on the left with a bunch of bounding boxes and convert it into weight? There's a lot of techniques you could try for this, but the point is the question is there, and the question is not necessarily straightforward. And that's one of the cool things that we definitely need to get to, because again, count is cool, but it's not that useful. Weight is when these businesses really start to take a look at your data and say, oh, that's useful to me. The good news is, despite all these challenges, despite how difficult this problem is, we are already unlocking big wins in this space. I mentioned 2 products that we build at Glacier at the beginning. Let me dive into those for a second. Number one is this computer vision enabled robot that can automate sorting, right? So if you attach one of these ML systems, look down at the belt, and can now all of a sudden classify everything that's coming down, you can now build mechanical systems that can do sortation at a high quality level, as high quality, as your ML model will allow you to go, and start getting to purity levels that these murphs were previously unable to achieve. Our robots today can actually divert over 50,000 items per day from landfill, and that's just with one robot. So it's really cool to see what this application can do in the real world, like the impact it can actually have. If you think about how things worked previously, again, on the bottom left there, you see what manual sortation looks like. As a reminder, it's expensive, it's hard to hire for, nobody really wants to work in this job, it's hard to retain, and it's actually unsafe. It's actually twice as dangerous as working in construction. If you think about it, it makes sense. You're sticking your limbs into a moving pile of who knows what. So yes, it tends to come with a couple injuries. That's obviously a ton of problems for these facilities, and something they're looking to get past. And that's where, robots are designed for the 3Ds, dull, dirty, dangerous. And this is absolutely the corner case in like, what is a dull, dirty, dangerous job? Our robots are, more affordable, they're more consistent, and they constantly obviously run, which is great. Number 2 is the analytics platform. So again, can you use that camera data to actually provide information to these facilities? One example that our cameras have done is they found over 80,000 items that are recyclable per day going to landfill from a waste stream. And that just kind of goes to show, like, yeah, there's a bunch of stuff we're throwing away, and we do have the ability to identify and capture it. We just need the technology to do it. If you're the facility and you hear that data, it's a no-brainer for you to start putting some collection techniques on the line that all those items are going to, so that you can actually prevent them from going to landfill and turn a profit on recapturing them. Again, as I mentioned before, the manual audits for doing this are super expensive. It takes 6 to 12 person hours to do a single audit, and therefore they happen almost never. As little as 12 months between. The highest I think we've ever heard is 2 months between. And so that's obviously not good for data, and the wins you can get out are certainly lacking versus a camera that just does this automatically using constantly processing ML, basically free to run, right? You pay for the thing and you pay for the computer to run, the electricity to run it, but beyond that, this is a pretty free machine, which is great. It's obviously super fast. It can just handle basically thousands of items in a minute. And it's always on. And so this is a big transfer, right? You're thinking about going from getting a data point once every 2 or 6 months to getting a data point every minute. And you are talking about a very, very different industry all of a sudden. This is what we've done so far. But as I kind of mentioned with this earlier graph, like there's a lot of stuff happening behind the scenes And therefore, there's a ton of opportunity for these applications to start making a dent on how the recycling industry operates and how efficient it is. I threw a bunch of magnifying glasses, but basically saying like, look, you can throw analytics on the consumer's recycling bin, right? As it dumps into the truck, what if you captured everything that was going in there? I'll give you an example of why that's valuable. In San Francisco, where our company is based, they are trying to enforce this fact that you should not put non-recyclables into your recycling bin or into your compost bin. But there's no way to enforce that, right? And so because there's no way to enforce it, nothing else gets done, and you end up with the same recycling rate that you had before. But if you could actually monitor in a really cheap way, just take a couple pictures of the trash as it's falling into the truck and say, okay, cool, here's everything I saw. This was the contamination rate of like this block or whatever it might be. All of a sudden, you can actually start taking action on factors and actors that are creating contamination in the system. Can you monitor what's going on inside the truck? Can you monitor what's going out of the murph, like the quality of the bales? If you're a reclaimer buying bales from a murph, you want to know that you're getting the quality that you promised, that you were promised. And so if they're selling you a 95% pure bale and you know there's 5% contamination, it pays to know that. And if you can know that very quickly, that helps you negotiate better and actually get a better deal for what you're getting. It obviously also pushes people to produce higher quality stuff. There's space for robotics in other parts of the chain, like in the reclaimer. There's space for analytics on the outbound of the reclaimer side. There's a lot of opportunity basically to apply this ML, this knowledge of where is stuff going, so that we can actually refine all of the rough edges on this system. Point being, big space, a lot of stuff to do, and we are certainly at the very beginning here with what ML, what AI can do inside the space, is why it's such a cool place to be. And I'd be remiss if I did not end this chat talking about climate change. That's, after all, why we're all here. This industry is crucial to climate, but in a way that surprised me when I dug in a little bit deeper. Over on the right, if your eyes didn't already jump there, is like kind of the big graph that I definitely got taken aback by when I saw it. But when we think about emissions, right, we oftentimes think about energy. We think about electrification, clean energy sources, and it is obviously super important to focus on that. But 45% of our emissions come from our stuff, our food, our products, our construction, and that stuff. The reason the emissions are there is highly due to the fact that we do not have a strong circular economy. I mentioned the emissions impact, the energy impact of using recycled material versus not. You can see how that bubbles up to a really significant chunk of our emissions. And as we look forward into the future, this gets bigger and bigger. Right now, today, plastics represents 8% of oil consumption. By 2050, we expect that to nearly triple. And so we're going to see this bubble get bigger and bigger. Unless we solve it in some major way, we will not get to a sustainable future. And this is why the circular economy is so important and oftentimes, frankly, overlooked. But there are a lot of problems and a lot of questions that we need to have answered. Knowing what products are causing those problems, knowing how much energy can I save if I implement XYZ law, how many CO2 tons of emissions can I prevent by opening up a new recycling plant? And fundamentally, how do we build a planet where we can ensure that nothing we have and nothing we consume is wasted? It's a really big challenge. We're definitely at the beginning of this journey, but it is really exciting and very, very important. That's why I am so excited to be here. Hopefully this was an informative talk for y'all. I'm going to open it up to Q&A. If you don't have any questions, that's how you can reach me. Feel free to shoot me an email. I love chatting with anybody who's interested in the space, interested in learning more. Reach out. Otherwise, we'll swap over to Q&A.
Fantastic. Thanks, Areeb. You may also win the award for best fonts. Presentation.
Right, I got all the superficial things taken care of.
But lots of deep content too.
Perfect.
And there's one question that floated up in the chat from Kenji, who's asking, are there any publicly available labeled data sets of items on murph conveyor belts?
It's a good question. Not that I know of right now. I know there's been a couple of universities who've done small experiments on this and created public data sets, but I think most of the data sets that I am aware of are not publicly available, which, you know, is a shame. It definitely should be something that's more public, so that more people can take advantage of it. But it's a great question and something that we should move towards as an industry for sure.
One of the things that popped out to me that just sounded super intimidating was sourcing one of these massive robots. And if I understand your background correctly, you're a software ML guy. Like, what was it like going into that physical domain and getting one of these whopping great things?
Yeah, it's the context there is my background is I used to be a software engineer, just like regular old front-end web software engineer at Facebook, and jumped into robotics somehow. It was quite an adventure for sure, Archie. I think I definitely leaned very heavily on my people. I knew a lot of roboticists and mechanical engineers that I could lean on and reach out to, and I would frequently have weeks where I would talk to like one different expert every single week, just kind of learning, hey, like, what do I do here? How do I solve this problem? The awesome news is, like, again, this space is something that everyone is really excited about. Everyone's really excited to help you out if you're working on climate. It's a really just like important place to be. I think everybody gets that. And so people were and still are definitely willing to give their time and give their thoughts to helping us get to a point where we actually could produce this thing. That being said, like, of course, the saying still stands, hardware is hard. It's a lot harder to build an industrial robot than it is to build an app. And that's certainly a pain, but at the end of the day, we're at a point right now where if you want to make real impact on the climate, my opinion is that you need to start building these hard solutions, because you need to interact with the world to actually affect the world. And that's the driving force behind it. Even though it's difficult, it really matters.
And so are you building these robots piece by piece, or are they commercially available elsewhere? Then you customize them? How does that work?
Yeah, so we build these robots in-house. They're obviously sourced from other manufacturers, but the design behind our robots is actually very specific to what recycling facilities need. You can use off-the-shelf robotics, but what we found time and time again talking to these facilities is there are these problems with these off-the-shelf robotics, whether it be the cost or the footprint, that just causes them to not quite be what these facilities need and not enough of a proof point. And so what we basically did is took all of those pain points and started from scratch and said, okay, if we had to design a robot specific to these recycling facilities, what would it look like? How would it operate? What would it cost? And let's build that machine. And so for that, we build a custom designed robot in-house.
Amazing. And I guess you're manufacturing them to order. You don't have a warehouse full of these.
Yeah, exactly. There are right now, hopefully we'll get there. We're still a young company, only 3 years old. But right now, every install is just a little bit different. So it's not yet at the point where it makes sense to kind of build out a big old warehouse and ship them out. So yeah, for now, that's the case. I think we want to get to a point in the future where that's not.
Incredible. Got another question from the audience, from Bill, who asks, do you get a sense from your work with MRFs about the future of plastic recycling? So obviously, Glacier's tech can help drive down some of the costs. There's a lot of FUD,
Yeah,
fear, uncertainty, doom. Is that
I'll
right?
take it.
These days about the fundamental viability of recycling at all.
Yeah,
Definitely. Thanks, Bill.
Definitely. This is a big, thank you for the clarification, Bill. This is a big question, right? Like, is recycling even a thing we need, or should we just ignore recycling, move towards some other future? And in my opinion, I would love to get to a point where we do not throw anything away. And everybody has their, like, oh, you can't see on my screen, their reusable water bottles, and like nobody wastes anything. But like, if we're gonna get to that world, we're not going to get there anytime soon. It's going to take decades to transition everybody over that. And B, frankly, like, that's a really hard thing to push on. If you're looking at 20 years of moving in that direction, what do you do with 20 years worth of waste that we're generating, especially when people are consuming more and more? All of the charts, all of the manufacturers, they all show single-use consumption isn't going away because people just don't seem to care that much. And so you can try to get around it, but in the meantime, I think it's absolutely a must that you do something about it, right? This stuff is still happening. The recycling is still necessary to deal with the evil that is. I would love to see a future where we don't need recycling, but I think even if that happens, it's going to be a long time from now. And so in the meantime, we definitely do need this, regardless of where we end up in the 100-year future.
Great. Bill, if you have any follow-up questions to that, feel free to put them in there.
He agrees. We're good.
I've got a couple of other technical ones. So you focused on the object detection piece. Is the control piece relatively solved now? Like in terms of actually then picking that thing up?
Yeah, absolutely not. No, it is not. That is a very hard challenge too. The task of picking up an item, that is like the holy grail of robotics, right? Picking up an arbitrary item in an arbitrary orientation. That is like the hardest thing you can do in robotics. So not only are we tackling a very difficult ML challenge, but we also have on our hands a very difficult robotics challenge. And so no, the controls thing is not yet solved. Within just like the scope of robotics, you have a fail rate, right? You attempt to go pick up an item and you fail to get it. And obviously we want to drive that fail rate down to zero, but it takes a lot of work to get the kind of precision, the kind of tooling on the end effector, and the kind of power you need to make that a reality. And there's a ton of cool, difficult, frustrating technical challenges tucked away in there.
I can imagine the dexterity you need to pick up a fine plastic film is insane. Like
it's tough. It's tough. Yeah, it's very tough. You can use suction to try to pick it up, but suction and film don't tend to go hand in hand, right? Because you'll get a clog pretty quickly. And so these robots, they struggle with that stuff. But these are solvable challenges. They just need to be worked on. And if you look at the amount of investments are like technical minds have given to this space, it's just like it's clearly not enough. But if we got enough people thinking about these problems, I'm confident we could actually solve them.
And is the detector running on local hardware? I guess so. It's not going to the cloud and coming back.
Yeah, the inference time needs to be kept pretty short, right? You're dealing with items moving down a belt at a pretty high speed. You could put the camera like, a long distance in front of the robot, sure, but then you run into a whole bunch of other complications, like how much space do you need? How much space does the facility have? Because of that, you end up with the camera as close to the robot. Therefore, inference, or the round trip time between taking the image and determining what the item is, needs to be very quick, and so that means inference is local.
Yeah, amazing. You got a lot of moving parts here.
Got a lot of moving parts. One of the cool things about building these robots is that the variety of engineers you need is just spectacular, right? Like back at Facebook, they called software engineers engineers, and like that was like, you're an engineer if you're a software engineer. And now I'm like, yo, we cannot be calling people engineers if they're a software engineer. That's a software engineer. This is a CV engineer. This is an electrical engineer, mechanical engineer, et cetera. And you have this whole spectrum working at the company together. It's really fascinating to see.
That's fantastic. Great. That's exhausted my bank of questions.
Perfect.
Are there any more from the audience? If not, I think all that remains is to thank you very much again for a fabulous talk. And
I look forward to my award for best funds.
Yeah, yeah, it won't be something you can throw away.
Perfect. I appreciate it. All right, Archie, thanks so much for putting this together. I love what you guys are doing.
Yeah, our pleasure. Thanks very much, Areeb.
Take care.
Bye.